There is one last interpretation for Cholesky's algorithm in the context of RKHS. Here is the question. H is given. On a set omega. This is given. And x0 is a point in X. And we consider this subspace, all the function in H, such that f at point x0 is equal to 0. It's easy to see that it's a closed subspace of H. And if we denote the kernel in H by K, what is the kernel here? Or, I mean, to distinguish KH, what is KH0? In a sense, we answered this question before by saying that KH0 is the projection of KH onto the space H0. True, that's the answer. But give me an explicit formula. This is what we want to do. And it's not easy, it's not difficult indeed to obtain this result by this observation. If you have M subspace generated by just one element, I mean, Y, a general Hilbert space, and Y is in H. So we consider all multiples of Y. It's a subspace. What is the projection onto M from H to H? There's a simple formula for that. The formula is this: the projection of X onto M. Of course, it has to be a multiple of Y, the projection to M. And what is the coefficient? The coefficient is this: X scalar Y divided by Y times Y, or normal Y squared. It's just now that the formula is given, it is easy to verify that PM is equal to PM star, and PM squared is equal to PM. Therefore, it's an orthogonal projection. And the range is precisely M, so it's the projection we are looking for. If the formula is not given, you may ask what is PM, but now that the formula is given, the verification is easy. So this part, I leave it for you, and this part I use. Why did I say this? Because my M, when the projection onto M is given, the projection onto the orthogonal complement of M, it would be I identity minus PM. This is the projection into M perp. So in other words, PM perp of X is identity times X minus a scalar times Y. That's the formula I need. What is my M? M in the context of now H is an RKHS and X0 is a point in X. My M is the space, one-dimensional space created by KX0. And when I mean in H. When I don't put the index, it means in the ambient space. So simply I write KX0. In this case, what would be mperp? Mperp is this all f in H such that f is orthogonal to kx0, which is the same as the space we are looking for. F orthogonal to this is equivalent to say that f at point x0 is equal to 0. True? And now projection into H0 is the same as projection to mperp is 1 minus projection into M. And we have the formula here. Therefore, what would be the projection into H0 of ky? This is equal to identity ky minus the other projection. Our formula is there, but note that y is kx0. So it's ky kx0 divided by kx0 kx0. Or if you wish, we can write it as ky minus this is k at point x0 x0. This is k at point x0 and y kx0. And this is precisely the thing we are looking for. I said at the beginning ky, but the kernel for the space H0 is precisely equal to the projection of ky onto that space. But we didn't know what's the formula. Now we know what's the formula. That's the formula we are looking for. And if we write it in the form of capital K H0 point xy is the same as little k index y at point x. So we evaluate both sides at point x. So this is the same as this one. Capital K H0 x and y is equal to capital K xy. Something you have seen before. K x0. But instead of putting this in front, we wrote it that way. We wrote it as k h0 xy is equal to kxy minus, we wrote this first, that's the kernel for the subspace of functions which vanish at point x0. Does this ring a bell? Pij minus pik pkj divided by pkk. We have seen this combination before, but in the finite dimensional case, our x0 is precisely the index k, and instead of x and y, we have I and j. So we obtain this by another method. This is a more direct method to say that the matrix that we obtained before is the kernel of the subspace of all vectors whose case component is equal to 0. x0 is equal to k. The k component is equal to 0 in that setting. So that's another interpretation. And this is a combination that we see quite often when we study the peak interpolation. So we should keep this in mind. Now, the remaining time, I talk a little bit about Shor, or sometimes called Hadamard product or multiplication. It's a very natural question, and it's difficult to answer this question when somebody from high school asks you, because my daughter have asked me this question, that when you have A and B, why don't you simply define A times B to be Aij, Bij, component by component? And or why when you multiply a row by a column and then for all rows of A and all columns of B? This looks more natural, and indeed it's a good product, which is called Hadamard product or Shor product. And in order not to mix it with the regular one, we use another notation. We put A or B, or a little circle home B, and it has many interesting properties, this Hadamard or Shor product. And contrary to the regular one, it's commutative. A on B is equal to B on A, and it has many more properties. It's already about 4 years, maybe 5, and still it goes on. Tom Ransford and myself have worked on polynomial approximation in weighted Dirichlet spaces. And our major tool, at least one of the major tools, but it's the most important one, is the formula for the Hadamard product of functions that we consider over there. Again, the same phenomenon we have in function space theory. If we have f of z sum n from 1 to infinity a n z n and gz well, we do f times g in regular product, or sometimes called Cauchy product. The first component is A0, B0, but the second is not A1, B1, is A0, B1 plus A1, B0, and so on. And when they go, we do the Cauchy product. And similar to the question above, a natural question is, why don't we define the product this way? If Ron is not good here, let's put a star. Indeed, a star is used for the Hadamard product over there. It's not composition, but the f star g is defined this way. And as I said, our major tool over there is to study f star g, the Hadamard product, and obtain some estimation which helped us to overcome the polynomial approximation question. Just as a comment over there that this type of multiplication makes sense in other domains too. And well, if somebody asks you, why don't we multiply matrices like that, or vectors like that, component by component, you immediately can say, well, of course we can, but it's another type of product and it has many interesting properties. And one of them, yes, we have time to see, we have still 13 minutes. I already explained about tensor product. Here is the short decomposition. Pretty much We have seen this good part of it, but there is one thing at the end which is needs more explanation. Sure, decomposition. We saw here as an outcome of Cholexy, but there is a little bit more here. Let P be an n times n matrix. If P is positive, I write like this instead of writing positive. Then there exists vectors. Then vectors in the book is V1 up to V1, V2, Vn in Cn, such that P is equal to the sum k from 1 up to n, vk star. This is the linear algebra notation. If you want to use the operator theory notation, this is the same thing as k from 1 up to n, vk tensor product vk. Is the same thing. In the first case, we have a matrix, a vector like this multiplied by its transpose. So the result is n by n matrix for each k. So this is vk, this is vk star. And you know, n by n matrix, add them all together, we obtain p. But we also, it is possible to interpret P as an operator on Cn. This is this version which is written here. And the action I defined before, just to repeat, the action of X tensor Y acting on Z is equal to inner product of Z and Y times the vector X. So here, X and Y, both of them are equal to VK. So that's the general case. So two versions of this. We saw this before indeed. We saw this decomposition. What is kind of new is that, moreover, any n by n matrix of the form P equal to the sum, and look here, I don't write up to n, I write up to m. M could be smaller or bigger than m. It's not necessarily equal to m. WK star, or if you wish, is positive. And the new part is here. Again, the fact that this is positive is immediate because every component here is positive, is invertible. If and only if the span of these vectors is the whole space. True. So we saw most of the theorem before as a consequence of Cholexy. decomposition theorem, P is equal to LL star, and LL star can be written in this form with VK playing is the case column. We saw this before. And each of these element here, WK star, is by itself positive, so the sum is positive. There's still nothing really new here. The only thing I need to explain a little bit here, why invertibility is equivalent to the fact that the span of W1 up to Wm is the whole space here. This is based on an interesting formula, is this one. So I just explained the last part. Proof if Z is in Cn, what's Pz in scalar Z, inner product with Z. Find a formula for this. And the formula either by this or by this. It's easy to get. P of Z, Z. What happens in the last 20 minutes of my lectures is something bad goes on. Last time when I stopped and came back again, it worked well. So I stop and go back again. Yes, that's good. So the inner product is, for example, if I use this, is equal to the sum k from 1 up to n, wk tensor wk acting on z and scalar with z. This is equal to the sum k from 1 up to n. By definition, the first component is by itself z inner product with k, z inner product with this one, times wk, then again inner with z. I can take the first one out. Take this out. And it's wk and z, which is the conjugate of the first one. So k from 1 up to n, absolute value of zwk squared. If I use this formula, I use this one. If you use, if you want to use the other one, you still obtain the same thing, but for the inner product of two vectors, the vectors say x and y, two vectors. Note that this is equal to y star times x. So y star is like that, x like this. We should use this, and still we obtain the same thing at the end. If we work with w star, I haven't done the calculation, but we can do it. P z z based on this, it would be z star times pz, which is z star sum k from 1 up to n, wk, wk, then wk star z. Take z inside, is zk, z star wk. And this one I can write z star WK star. So it's the same thing as ZWK, and note that this is a complex number. So it's become Z star WK, and finally we obtain the same formula as before. This is what I obtained here too. Well, doesn't matter Z or Z scalar WK or WK scalar Z is the same because it's inside the absolute value. So at the end of the day, I have PZ scalar Z is equal to the sum absolute value of ZWK then squared. That's the formula. So another thing to consider is that the null space of P, which is the point Z such that PZ is equal to 0, is also the same as the point Z such that PZ and Z equal to 0. Right. This is a good exercise for you. Of course, if P of Z is equal to 0, this one is equal to 0. But why from PZ scalar Z equal to 0, we can conclude that PZ is equal to 0. It's a good exercise. I leave it for you to do it. And therefore, now the green box formula helps us to see what is the null space of P. PZ scalar Z is 0 if and only if every one of these is equal to 0. So it's the same as all Z such that ZW1, Z scalar W2, Z scalar Wn equal to 0. Or put it this way, Z equal to all the points Z is orthogonal to W1, Z is orthogonal to Wm, or span of W1 up to Wm perp. So that's another formula, N of P. Well, don't need to repeat it. It's there. What is NP perp? In the general case is the range of P star, but P here is how to say auto-adjoint, self-adjoint. It's self-adjoint, so it's R of P. And if we take the perp of both sides and considering the fact that in the finite dimensional case, everything is closed, so R of P is equal to simply a span and a vector P, an operator T from Cn to Cn is one of the basic and important facts in linear algebra, for which we can use this formula or the formula for n of p. The fact is that p is invertible if and only if p is injective. This is the same as n of p is equal to 0. If and only if p is surjective. This range of p is equal to Cn. That's a standard but important fact in linear algebra. And therefore, by this green formula, or for the formula for the null space of P, we immediately see that, therefore, P is invertible, which in our case is equivalent to see that, to say that P is strictly bigger than 0, because it's already bigger than or equal. We want to exclude equality. And this is equivalent by the green formula that the span of W1 up to Wm is equal to Cn. That's a kind of nice theorem of Schur. And again, another immediate consequence of that is this one. So here is theorem. Here in the Schur or Schur product. Let P and Q be n by n matrices. If both of them are positive, then the product is positive. If P bigger than or equal to 0, Q bigger than or equal to 0, then P rond Q, the Schur product, is positive. That's number one. And number two, if both of them are strictly positive, then the Schur product is strictly positive. Which, if you apply the original definition, is not that obvious. Recall the original definition of P being strictly positive and Q being strictly positive. This I will erase, but I repeat. This means that the sum alpha I bar alpha j Pij is bigger than 0. The other one is for Q. And now from this, we want to conclude that the sum for any eta of product is again positive. Absolutely non-trivial. Absolutely. I invite you to sit and try to use this original definition to see if you arrive at this. And now we see the advantage of working with different representations. Each representation has its own merit if it gives us some information. We saw the Schur decomposition. Now let's see an application for that. Proof. By previous theorem, we know that P is given by a sum, say I, oh, let's use K, K from 1 up to M. Is it use here? Use V, okay. VK star, or if you wish, operator theory notation. And the same for Q. L from 1 up to another, I mean, M prime, WK star, oh, WL star, WL tensor WL. And what would be P composed with Q, P rond Q, the short product? It is distributive. It will be the sum over K, sum over L of, I mean, add up one of this notation. For example, I just write the first one to favor linear algebra, VK star on WL star. We are almost done if you pay attention to what this means. We have a vector here, we multiply by its transpose, then component by component. We do the same with W. So this is V, this is W. And then we do the short product component by component. If you write the formula, and that's the simple but the key observation, to see that this is precisely equal to if you do VK rond WL, which means that you do the short product for V and W. That becomes a vector. Then VK rond WL star. That's, and then we are done. Then we are done because you have a vector here multiplied by its transpose. It's something positive. Sum of positive things is positive. So this immediately implies first part because every term is positive. Just a simple observation. If you have the decomposition, then and let me also write with the second language, the language of operator theory, because sometimes we might use it. The same P rond Q is sum K from 1 up to M, VK tensor product VK, L from 1 up to M prime, the same thing for W. This is precisely what I wrote before, but with a different notation. It becomes distributive, sum over K, sum over L, VK tensor VK, then WK tensor WK. And this is as before. It's the same thing as VK short product WK, WL. Tensor, the same thing, VK or WL. So we obtain the same thing as before, but it is slightly different language. And X tensor X is something positive, sum of positive thing is positive, so we obtain again number 1 with the second representation. For the second, if both of them are positive, then why the short product is positive, we use this one. P is invertible if and only if the span of the vector is the whole space. And our vector now, we know what they are. All of this. K goes from 1 to M, L goes from 1 to M prime. So to answer 2, we need to study the span of our vectors Pk tensor WL when K is from 1 up to M and L is from 1 up to M prime. What is this span? Let me write it this way to be more clear. I have V1 tensor W1, V1 tensor W2, and V1 tensor Vm prime. And the same thing for V2. Vm prime, and finally the same thing with Vm. These are my elements. W M prime. And a span means that you multiply each of these by a constant and add them up. You can put the constant in front, you can put the constant with the first one, you can put the constant with the second one. And when you add, you immediately see that this is indeed equal, but at least you agree that it includes the when I multiply the first one by a constant and I put the constant with W, and the second one by another constant, I put the constant with W2, and also the last one I put it with W V prime, and do the summation. It will be V1 tensor span of W1 up to Wn. And I do the same with the second row. It will be V2 tensor, the same thing, and Vm tensor, the same thing. All of these are in my space. Everybody agrees up to here. And now I use this assumption. Q positive. Q strictly positive. A strictly positive means that the span is equal to Cn, so it's a span of V1 tensor Cn. You understand what tensor Cn means? Means any vector in Cn up to Vm tensor Cn. Anything I want, I can create here because Q is positive. Anything. In particular, I can create eta equal to 1, 1, 1 transpose. I mean, I usually, let's keep our tradition. We usually write a vector like this. I can create a vector, all its elements equal to 1. So I choose my combination here to create eta, the same here, I create eta, the same here, I create eta. So it will be a span. What is V1 tensor with eta? If you look carefully, either with, indeed, here is the case that I should have write it with with this notation. This notation is better, but still it works. It is V1, V2, and Vm. And now I use the fact that P is strictly positive. This is equal to Cm because P is strictly positive. And the conclusion is that POQ is strictly positive. That's the end of story. So if both VK and WK span the whole space, either the tensor product or this notation VK star, WL, W star, all of these vectors create the whole space, and we are done. Just check if I wrote everything correctly. Yes, everything is fine. Okay. So this shows that if both of them are strictly positive, then the short product is also strictly positive. And that finishes this section. Next week, we start to talk about tensor product. The explanation in the book, I mean, they didn't go into detail. I've prepared a small text to explain what is the tensor product of Hilbert spaces and why we obtain an inner product in the tensor product. And then we use this to study some spaces like, Bargman, not Bergman, Bargman space or Drury-Arverson space. They are important in application. And indeed, in 2 weeks, next week indeed, we talk about non-commutative, yes, in 2 weeks. And the week after, we talk about the whole session is about Drury spaces. So it will be a good preparation for the week after. Michael Hartz will talk about such spaces. Okay, thank you very much. Thank you.